Every data point tells a story, and tracing that story is the first step toward credibility. Knowing the source, collection method, and freshness date reveals how much weight the information deserves. A cost figure from last quarter is not equivalent to one from 5 years ago. A vendor's brochure is not as trustworthy as an audited report. Traceability allows analysts to grade confidence, separating sturdy facts from shaky ones. In practice, this means documenting who gathered the data, when it was last verified, and under what conditions. Fresh, transparent inputs let others retrace reasoning later without doubt or surprise. Strong analysis also distinguishes measured data from judgment-based estimates. Numbers derived from instruments, logs, or sensors carry different uncertainty than those derived from expert intuition. Both have value, but they belong in separate lanes. Treating opinion as measurement compresses reality and hides variance. A project manager's roughly 6 months differs from a schedule drawn from recorded durations across 10 similar projects. When these distinctions are explicit, models can assign appropriate confidence levels. Blending them blindly invites error masquerading as precision, a common cause of misplaced faith in spreadsheets and simulations. Human bias lurks behind much of this problem. Optimism bias makes people expect the best. Anchoring bias tethers new estimates to early guesses. Availability bias exaggerates whatever examples are easiest to recall. Together, they create data that look confident but lean hopeful. Recognizing these biases requires humility and process. Ask how an estimate was formed, what examples informed it, and whether alternate outcomes were considered. Encourage participants to imagine plausible downside scenarios, not just preferred ones. Training teams to notice these tendencies inoculates analysis from the quiet distortions of human nature. Reference classes help restore realism. Instead of relying solely on memory, analysts compare the current effort to a class of similar past projects. This outside view anchors judgment in historical distribution rather than wishful thinking. If 10 comparable projects averaged 20% overrun, the 11th is unlikely to be different without clear evidence. Reference classes also expose recurring patterns that individual memories miss. They reveal how uncertainty behaves at scale and where past optimism bloomed unchecked. By grounding new estimates in empirical history, reference classes turn experience into evidence. When seeking estimates, start with ranges, not points. Asking someone for a single value invites overconfidence. Asking for a low and high bound invites reflection. Ranges acknowledge that uncertainty is normal and encourage contributors to consider variability explicitly. The process itself is educational. It makes uncertainty visible rather than hidden beneath false exactness. A credible range signals thoughtful engagement. A suspiciously narrow one usually signals guesswork. Models built from ranges breathe with realism. They move within plausible boundaries rather than pretending those boundaries do not exist. A particularly effective calibration tool is the 90% confidence question. Ask contributors to state a range within which they are 90% sure the true value lies. Most people underestimate how wide that should be. After repeated exercises, they learn to widen or tighten appropriately, improving self-awareness of uncertainty. Over time, this habit trains judgment like muscle memory. A well-calibrated expert is not the one who is always right, but the one whose stated confidence matches reality. This alignment between belief and outcome is the foundation of trustworthy forecasting. Disagreement among experts is inevitable and valuable, provided it is resolved through evidence, not authority. When estimates diverge, review the assumptions and data behind each. Often, differences arise not from error, but from different mental models of the situation. A structured evidence review, comparing data sources, definitions, and contexts, can reconcile these perspectives. The goal is not compromise for its own sake, but convergence around justified reasoning. Consensus built this way becomes robust because it survives scrutiny. Disagreement handled poorly breeds confusion. Handled well, it sharpens understanding. Outliers deserve special attention. When one input sits far from the others, document why. Perhaps it reflects a genuine anomaly, or perhaps it signals a measurement problem. Writing down the rationale forces reflection and protects institutional memory. Months later, when the number resurfaces, readers can trace the reasoning without guesswork. Outlier documentation also prevents analysts from quietly discarding inconvenient data, a subtle but dangerous form of confirmation bias. Clear annotation turns outliers from irritants into teaching moments about system variability and data integrity. Cross-checking against historical analogs keeps analysis honest. Whenever possible, compare new estimates to results from past projects of similar scale or scope. If predicted costs, durations, or defect rates fall well outside historical norms, probe why. Perhaps genuine innovation justifies the difference, or perhaps assumptions slipped out of reality's orbit. Historical benchmarking grounds imagination in evidence. It also builds an institutional feedback loop where every project enriches the next with better data and tempered expectations. Without that loop, each effort starts from scratch, repeating the same misjudgments in new wrappers. Backtesting converts hindsight into calibration. By comparing prior forecasts to actual outcomes, teams see where confidence was misplaced. Did a 50% probability really occur half the time? Did optimistic durations repeat across multiple projects? Backtesting does not punish, it educates. It replaces intuition with feedback. Patterns of consistent bias reveal where data gathering or estimation culture needs repair. Over time, this practice raises both accuracy and humility, traits that transform raw analytics into disciplined forecasting. No data set remains stable forever. Market prices shift, technologies evolve, and organizations change processes. Detecting drift means periodically checking whether established scales or conversion factors still represent reality. A productivity index built 5 years ago might no longer reflect current tools or workforce capability. Adjusting scales when drift appears keeps models aligned with the present. Ignoring it embeds outdated assumptions that corrode analysis quietly from within. Calibration, like maintenance, prevents degradation before it becomes visible failure. A lightweight calibration routine keeps quality habits alive without slowing the work. It might include quarterly spot checks of key metrics, quick team sessions to compare perceived versus actual accuracy, or a small repository of historical baselines. The emphasis is on rhythm, not bureaucracy. Regular exposure to feedback builds natural awareness of uncertainty. Over time, participants internalize the discipline, estimating with quiet confidence rather than guesswork. The process becomes part of professional hygiene, an expected element of responsible analysis, not an extra chore. Data quality, ultimately, is not about volume but about trustworthiness. Hundreds of figures cannot outweigh a single well-calibrated insight grounded in evidence. Quality beats quantity every time because decisions run on reliability, not decoration. Models built on sound data guide teams with clarity and composure. Those fed by weak inputs mislead, no matter how sophisticated their mathematics. Calibration is the compass adjustment that ensures every step forward aligns with truth. Without it, the most advanced analytics wander off course, chasing precision while losing accuracy. Thanks for listening. For more audio courses, daily newsletters, and more, please visit baremetalcyber.com.